Hello everybody, how's everybody doing? CRS here. In this video, we will be solving a lot of questions that are pertaining to the chapter wave optics, and these questions are most probably going to occur in your board exam. So let's have a look at each one of them one by one. Let's begin with the first question. Here goes the first question. In a Young's double slit experiment, the distance between the slits is 1 mm. In Young's double slit experiment, distance between the two slits through which the light comes out is denoted by small d, and it is given to be 1 mm. 1 mm is 10 to the power of minus 3 meter. The fringe width is found to be 0.6 mm. So beta is how we denote fringe width, and that is 0.6 mm. 0.6 milli is 10 to the power of minus 3 meter. When the screen is moved through a distance of 0.25 meter away from the slits, so the new distance between the plane of the slits and the screen is increased by 0.25 mm. So 0.25 meter. Whatever is the initial distance between the plane of the slits and the screen, that has been incremented by an amount 0.25 meter, right? Away from the slits, it's away, so the distance has increased. That's what makes me write a plus sign here. The fringe width becomes 0.75 mm. The new fringe width becomes 0.75 millimeter. Milli is again 10 to the power of minus 3 meter. Find the wavelength of light used. We need to find the wavelength of light used. With the given data, my friends, we know that the fringe width is given by beta, which is equal to capital D lambda divided by d, where beta is the fringe width, d is the distance between the slits and the screen, lambda is the wavelength of light used, small d is the distance between the two slits through which the light comes out and interferes. The same formula can be written for another situation. When you increase the distance between the plane of the slits and the screen, you can write it as beta dash equal to d dash lambda divided by d. I'd like to subtract both of these equations. Let's do beta dash minus beta. Let's see what you get. Lambda by d can be pulled out as a common factor. You will have d dash minus d. When that is the situation, let's substitute this. Beta dash is 0.75 minus beta is 0.6. And then there is a 10 to the power of minus 3 associated with both of them. Look at this. You can pull that out as a common factor. So it becomes 10 to the power of minus 3 equal to lambda. Lambda has to be figured out. Divided by small d is 10 to the power of minus 3 multiplied by d dash minus d. D dash is d plus 0.25 minus d. So we have plus d and minus d getting cancelled. So we have 0.15 multiplied by 10 to the power of minus 3 equal to, we have 0.25 can be written as 1 by 4 into 10 to the power of minus 3. 0.25 is 1 by 4. That's lambda. So what does lambda become equal to? Lambda becomes equal to 4 into 0.15 is 0.6 into 10 to the power of minus 6. Well, you can write it in nanometer. You can write this by shifting the decimal place 3 times further and write it as 10 to the power of minus 9 meter, which can also be written as 600 nanometer, and that happens to be your final answer. It's as simple as that to crack this question. Let's look at the next one. Let us look at the next question. In Young's double slit experiment, by using a source of light of wavelength 4500 angstrom, so lambda has been given to us. It's 4500 angstrom, which can be written as 4.5 into 10 to the power of minus 7 meter. The fringe width is 0.5 mm. The fringe width becomes 5 millimeter, 10 to the power of minus 3 meter it is, if the distance between the screen and the plane of the slits is reduced to half. That means the distance between the plane of the slits and the screen in the second case is 1/2 of the distance between the plane of the slits and the screen in the first case. Then if you need to get the fringe width, the question is, what should be the wavelength of light to get the fringe width of 4 mm? So you want to get a fringe width of 4 mm now. So maybe we should call this wavelength lambda 1 and this the initial fringe width beta 1, we need to find the wavelength of light in the second case in order to get this fringe width, which is 4 into 10 to the power of minus 3. We know that the fringe width beta is given by d lambda divided by d. The small d is the distance between the slits, distance between the two slits, and that remains a constant. If that is the case, you can establish a proportionality for lambda. Lambda is directly proportional to beta and is inversely proportional to d. Well, that's only a mathematical way of saying it. Because lambda is the source of light, that remains a constant unless you change the medium. When that is the situation, we have lambda 2 divided by lambda 1, my friends, being equal to beta 2 divided by beta 1 multiplied by d1 divided by d2. So this is what you have. We can now substitute lambda 2 divided by lambda 1 is 4.5 into 10 to the power of minus 7 equal to beta 2 divided by beta 1, which is 4 into 10 to the power of minus 3 divided by 5 into 10 to the power of minus 3, 10 to the power of minus 3 multiplied by okay, d1 divided by d2. d1 divided by d2 is going to be 2. So you can simply from here imply that d1 divided by d2 would become equal to 2. So you can simply say that this is equal to 2, right? Well, lambda 2 would become equal to 4 into 2 is 8. 8 into 4.5 is going to be 36, 3.6 by the way, into 36 into 10 to the power of minus 7 divided by 5. 36 divided by 5 would turn out to be 7.2 into 10 to the power of minus 7, which can be written as 720 nanometer. So that is the answer to the question. So it's as simple as that. Let's go ahead. Let's look at the next question. Calculate the distance between the 5th and the 15th bright fringe. So N5 is 5, it's the 5th bright fringe, and let me write the 15th bright fringe's number as 15, right? In an interference pattern obtained by an experiment due to narrow slits separated by a distance 0.2 mm. Small d is 0.2 millimeter, milli is 10 to the power of minus 3 meter, and that is the case. And it is illuminated by a light of wavelength 560 nanometer is 10 to the power of minus 9 meter. The distance between the slits and the screen is 1 meter. We need to find what is the distance between the 5th bright fringe and the 15th bright fringe. So I'll just write that as delta x, and it is expressed as x15 minus x5, right? That's exactly what we got to calculate. We will calculate this. Now, xn is the distance to the nth bright fringe. And how do you calculate that? Distance to the nth bright fringe is n d lambda divided by small d. When that is the case, we have x15 minus x5 would become equal to n15 minus n5 multiplied by d lambda divided by d. All this x15 minus x5 is delta x. That's exactly what we've got to find. So delta x becomes equal to 15 minus 5 multiplied by d is 1 meter. Lambda is 560 nanometer divided by small d. Small d is 0.2 millimeter. So you work this out and it will turn out that the answer is 28 into 10 to the power of minus 3 meter, which can certainly be written as 28 millimeter. That's your final answer. Such questions will keep coming in your board exams. Practice. Let's go further. Let's look at the next question. In Young's double slit experiment, the wavelength of light used is 5000 angstrom. So the wavelength of light has been given to us. 5000 angstrom can be written as 5 into 10 to the power of minus 7 meter. Distance between the slits is 2 mm. Small d has been given to us. That's 2 mm, 2 into 10 to the power of minus 3 meter. The distance between the screen from the slits is 1 meter, capital D. The distance between the slits and the screen is 1 meter. Find the fringe width. Also calculate. We have to find the fringe width, right? Also calculate the distance of the seventh dark fringe, we need to calculate the distance to the seventh dark fringe. I'll write it as 7D, right? Seventh dark fringe from the central bright fringe. Let's find one by one. Quite simple a question here. Beta is fringe width and it is given by d lambda divided by small d, and that is equal to 1 meter multiplied by lambda is 5 into 10 to the power of minus 7 divided by small d is 2 into 10 to the power of minus 3. So the answer you would get beta would be 2.5 into 10 to the power of minus 4 meter. That's the answer for fringe width. Well, you can also write it as 0.25, right? If you want to write it as 0.25 mm, it's perfectly all right. Next, we need to find the distance to the seventh dark fringe. Now, the distance to the dark fringe is given by 2n minus 1 lambda d divided by 2d. That's how you calculate it. Now, lambda d by d is anyway beta. So you can certainly write this as x and dark fringe, so nd if you like. So x nd would simply be equal to 2n minus 1 divided by 2 multiplied by beta is how you can write it. And substitute for beta, and n is 7, my friends, because the question says we need to find the distance to the seventh dark fringe. When you write 2n minus 1, you will have to substitute n equal to 7, but if in case you end up writing 2n plus 1, then you will have to substitute 1 less than the number. That means if you want the distance to the seventh dark fringe, you will have to substitute n equal to 6. As simple as that. So we have 2n minus 1 here. We will be directly substituting. It is 2 multiplied by 7 minus 1 divided by 2 multiplied by beta is 0.25 millimeter into 10 to the power of minus 3. It's 2.5. I told you about it. So we have the distance to the seventh dark fringe becoming equal to 1.625 millimeter. Right? This is 5. 1.625 millimeter is your answer, and that's the complete solution to the problem. Practice this. Let's go further. Let's look at the next question. In Young's double slit experiment, two slits are illuminated by dichromatic light. So on the Young's double slit experiment apparatus, two wavelengths are incident simultaneously. The first wavelength, my friends, let me write that as lambda 1, and it is 750 nanometer. And the second wavelength that is incident on it is 600 nanometer. If the distance between the slits is 2 mm, small d is given to us, that's 2 mm, mm is 10 to the power of minus 3 meter, and the distance between the slits and the screen, capital D, is 2 meter, at what minimum distance from the central bright fringe will a bright fringe from the interference pattern coincide with the bright fringe from the other? So let's try and understand the question. In the Young's double slit experiment, on the two slits, there are two wavelengths that are incident, so there will be two interference patterns. The one interference pattern which is narrower will be of the wavelength which is smaller, essentially 600 nanometer. Another fringe pattern will be wider, and that would be due to 750 nanometer wavelength, right? Because of this difference, there would be some place other than the central bright fringe coinciding. The central bright fringes will coincide for sure, but other than that, if you go further and further away from the central bright fringe on the screen, there will be another place where the distance, where the bright fringes, due to both the fringe patterns, would coincide, and we will do exactly that. Let us say that the nth bright fringe due to first wavelength, right? Or maybe you can just write this as nm, n wavelength, and this can be written as wavelength, right? So maybe, all right. So there we are. This is mth wavelength, right? That's the mth wavelength. The distance to the nth wavelength from the central bright fringe is equal to distance to the mth bright fringe in the other pattern on the same screen. Only when these two distances are equal, that means they both of them are coinciding. Only when they coincide will the distance between them will be the same. Of course, the first coincidence will occur with the central bright fringe. This is the next one, and you can have more of these as in when you go further in the fringe pattern. Xn is n lambda n d divided by small d, and here you will have m lambda m d divided by small d. Do you see d by d gets cancelled on both sides? So we have n lambda n divided by n lambda n equal to m lambda m is all you will have. So what does n divided by m become equal to? It becomes equal to lambda m by lambda n. It becomes equal to lambda m by lambda n. When that is the situation, you just substitute it here. When you substitute it here, lambda m is 600 nanometer, and this is 750 into 10 to the power of minus 9 meter. You will see the zeros will go away. All you will have is n divided by m. This is going to be 4 and this is going to be 5. N by m is 4 by 5. Let's try and understand what this means. It means that the fourth bright fringe due to this wavelength coincides with fifth bright fringe of this wavelength, because it's n by m. N corresponds to lambda n and m corresponds to lambda m. So the next coincidence will occur like this. The eighth bright fringe of lambda n will coincide with 10th bright fringe of lambda m. So if you are writing an equation for distance to the nth bright fringe, for the first wavelength, let's say xn, I shall write, it would be nd lambda divided by small d. You will have to take 4, n equal to 4, if you are writing the nth wavelength. So that's lambda n. D, my dear friends, is given in the question. It's 2 multiplied by lambda n is 750 into 10 to the power of minus 9 divided by d, small d would be 2. This gets cancelled, and you will see that this is 4 into 750, that's basically 3000, right? 3000 into 10 to the power of minus 9, and there is 2 into 10 to the power of minus 3 that I missed out. So simplify this and you should get 3 millimeter, and there is a 10 to the power of 3 here. 3 millimeter is the answer. So at a distance of 3 millimeter, the fourth bright fringe of 750 nanometer will coincide with fifth bright fringe of 600 nanometer, and that's the answer to that question. If you learn these many questions, I am sure you will be able to answer almost any question that will appear in your board paper, and I wish you all the best with respect to wave optics learning, and practice these numericals. I am sure you will come out with flying colors. But do remember, the day you stop growing is the day you start decaying. Thank you so much.